Hello everyone. In this video, we are going to talk about strain energy, which is one of the topics in solid mechanics. So strain energy is the energy that you use to deform a material, okay, some part. So if we look at the force versus deformation or the change in shape, if we can plot this, the area under the curve is clearly that the strain energy, which is clearly equal to the work done by the external forces. Now, the strain energy density is that energy per volume. So if I divide the integral of FdL by volume and assume that this is like a prismatic object, A times L, then this F over A is sigma dL over L is the epsilon. So I can say that the energy density for strain energy density is the area under the curve of stress versus strain, okay? So these are two notions. And of course, the unit for strain energy is joules. And for this one, it is joules per like meter cubed or per feet cubed. Okay, so that is the definition of it. Now, when material undergoes elastic deformation, you know that it goes up here and then goes down on the same path, goes back to whatever it was, it's elastic. So all of the energy that you use to deform it, it is going to store it and then give it back to you. So the material acts just like a perfect spring. But if you go into the nonlinear region and here you unload, you go back to zero force but not zero strain, and this line is parallel to the linear region. And so you're going to get some permanent deformation and permanent strain. And this energy, which is area under the curve of this area here, is something you would never get back, because that one is used to deform the object. So that is a dissipated energy. Now, a portion of it might be used to generate heat or sound wave or anything, but a good portion of it is used to deform the object. Okay? Now, if we only look at the elastic region and also linear as well, then calculating that area under the curve is very easy, because the area under the curve is a triangle. So if I have sigma at any point and epsilon at any point, if I go up to the level sigma and epsilon and go back, right, or just keep it at that level, clearly the area under the curve is width times height divided by 2. So it's sigma epsilon over 2. And that's very easy. Or you can write it as sigma squared over 2e, or e squared, e times epsilon squared over 2, because the slope of this line is e. Okay? So in the linear region, or linear elastic region, this strain energy density is a very simple formula. Now, let's look at a few cases of the deformations that we have studied in previous videos, and then we're going to look at the 2D case, and then we're going to see an application of this notion. So if we had the axial load on a prismatic bar, correct? So we have this prismatic bar, and the length of it is L, the cross section is A, and I'm applying force F on both sides, or one side is fixed. Then the total strain energy, which is equal to the strain energy density times volume, is going to be, for the density, we're going to plug in sigma epsilon over 2 for volume A times L, and then A times sigma epsilon times L. Epsilon times L is the total elongation, and sigma times A is F. And if you remember, for this prismatic bar axial load, the change in the length, if you watch my axial load deformation video, it was F times L over AE. So I'm going to plug it right here. And this 2 here is not the power, it's 2 times. So let me bring it back if it's confusing. That 2 is just that 2 that you always had in the denominator. This FL over EA, that is your delta L. So the total energy is going to be F squared L over 2 EA. That is what we have for the total strain energy. Now, sometimes this A changes as you move along the X direction. It doesn't have a fixed cross section, or the force changes along the bar. In that case, instead of this constant formula, you can integrate that same entity over the length, except for D for L, use dx. So you consider a short, small element, and over that element is what you calculate this term, and then multiply by dx to calculate the d of that u, and then integrate du from 0 to L to get to the entire energy. Now, if a shaft is under torsion, so you applied some torque here, and you know at the end it is going to go through angle phi, the angle of twist, then integral of T d phi is the total strain energy in the linear region. So since it's linear, you can write it as T phi over 2, and remember phi for the torsion, it was TL over GJ, so you simplify, you're going to get T squared L over 2GJ. Again, if this polar moment or this torque or both of them are functions of x and not constant, you can simply integrate that from 0 to L to get the entire strain energy. And if the beam is in bending, and here we talk about pure bending, so if you have pure bending here, and it goes and comes to one single center of curvature, O, and these are rho, and this angle is theta, and this length is L, then, and these moments are M, then the total energy is going to be integral of m d theta. Since m is constant, you bring it out, and it's a linear relation, so it's going to be m theta over 2. Now, theta, remember, in pure bending was L over rho, and 1 over rho, if you remember, in bending, 1 over rho was m over EI, okay? Or it was K, kappa. So look back at the videos, you're going to find it. So just multiply it by L. That is going to be the total angle, right? And here multiplied and simplified, you're going to get m squared L over 2EI. Okay? Now, if m or I are variable with time and it's not pure bending, then you're going to do this integral to get the total energy, strain energy of a beam in bending, which is not pure bending, because m here can change versus time, and I could or could not change versus position. Sorry, not versus time. So these are different formulas for torsion, for bending, for tension and compression or axial load. Whether it's variable or constant, we have formulas for each and every one of them. Now, if it's a 2D case of stress, right? So here you have sigma x and sigma y and tau xy. In this case, what you need to do, you need to calculate the energy for each and every one of them and add them together. So for sigma x is going to be sigma x epsilon x over 2. For sigma y, similar. Now for the shear stress, it's going to be the stress times the strain over 2, just like these other ones. Okay? So this is the total energy density that you have in 2D case. Now here, I'm going to use the Hooke's law. If you remember, we are going to use the Hooke's law, and we are going to replace these epsilons and gammas by their dependency on the stresses. So if you remember, this gamma here is tau xy over g. So if you replace it, you're going to get this term. And epsilon x was what? Epsilon x was sigma x over E minus nu times sigma y, epsilon y, which was sigma y over E. And nu was the Poisson's ratio. And similarly, epsilon y was sigma y over E minus nu sigma x over E. So if you plug these up there, you can write it all based on the stress terms. and Poisson ratio, and of course this shear term. Or if you do the other way, you write the stresses here based on the strains and write everything as function of strains. This is what you get in terms of all the strains. So depending on what you have, you can use one of these formulas. If you have both of them, you can use the first one. If you only have measurements of stress, you can use this one. Most of the time, you only have measurements of strains. You have strain gauges. I have a video on it. Go watch it on strain gauges. And all you can measure are these guys mostly. So you can use this last formula. Okay, and that is exactly our next example. So here I have an aluminum plate, and I attach two strain gauges, A and B. A measures a strain along X, B measures a strain along Y. And the values they recorded are these two numbers. Now the plate does not have any shear strain or stress in it. And for aluminum, the Young modulus and the Poisson's ratio are these numbers. So now with all of that in mind, we want to find the amount of strain energy in density, of course, strain energy density in these aluminum parts, right? So here we're going to use this last formula and say U equals basically E over 2 times 1 minus nu squared and epsilon x squared plus epsilon y squared plus 2 nu product of the epsilons and shear in 0 in this case. So that's all you have. And E is given, nu is given, epsilons are given, everything is given. So from here, you should be able to easily calculate this. And the number that you will get is going to be 8.96 psi. Okay, so you can easily find it. Now, if you had some way to measure the shear strain, if you had the shear strain gauges, you could also, if there was any, you could measure gamma and then plug it in and find the thing. Now, if somebody says, what is the total energy, right? If somebody says, what is the total energy in this case, all you need to do is to multiply this by the volume. So if I have these dimensions, if I have this A, B, and the thickness of this guy, T, then I could simply what? I could simply multiply it by A times B times T, and that is going to be this the entire energy stored in the aluminum plate as a result of this loading. Okay? Now, you might say, fine, all good and everything. How would you use this other than, fine, we calculated some energy or something? Is there any application to it? And the answer is yes. Now, here I'm going to show you an example of how to use it, but in my next video, which is on Castigliano's theorem, I'm going to use this notion of strain energy, and we are going to find displacement in different structures in a more basically systematic way, systematic approach. So this video and this example, you can consider it as a precursor to my next video, okay? Here, I just want to introduce you to the notion of strain energy and show you an application, but ultimately, we look at the application of it more in the next video. So what is it? Here I have a truss, ABC, and AC, you can consider it like a fixed member, so that's the simplest 2D truss. Both of these members have length L, which is not given, but you can find it based on angle beta and height H that are given. Here I apply the force P downward, and I want to know how much this point B is going to go down as a result of this load. Consider this material to be made from something with Young modulus of E, and consider the cross-section to be A. So we don't give any specific material or anything. This is completely parametric. But if the geometry is given, if the material cross-section is given, if the loading is given, we want to find the displacement of point B, basically, which is going to be downward in this case, of course. The question is, how much is this? So the way we do it is we calculate the strain energy in these two members and set it equal to the work done by this force P. Now the question is, what is the work done by force P if point B goes down by delta? Well, the work done is clearly going to be P times delta B over 2. Remember, we are working in the linear region, so the work done or the strain energy is going to be force times displacement divided by 2, okay? Because it behaves a linear manner, so area under the curve is going to be a triangle, and there is always a 2. So this is the work done by this P. Now, how much strain energy is going to be stored in them? You know, when you apply this P, these members will be subjected to axial loading, right? These are two force members. Here, the weights are negligible, and it's a truss. So each one of them is going to be subjected to some axial load, and each one will have some elongation. As a result of that, there will be some energy stored in each one of them. If you add those two energies together, the total energy, that should be equal to this work. Okay, so the thing is, how do we find U1 and U2 and add them together, and let's see if it can help. So the first thing is, how much is the axial load F in each one of these members? Well, clearly here at point P, we have to have a static equilibrium. So if these members are being in tension with force F, then the force F at point P is going to be applied backward to the pin, as well as that load P downward. And remember, these angles are beta each, and clearly there is equilibrium here. In the x direction, they would cancel each other. In the y direction, clearly you can see that if you write some Fy, that is going to be 2 times F times cosine of beta. This should be equal to P. And from here, you can find the axial load in each member. It's going to be P over 2 times cosine beta. Now, what's the length of each member here? Clearly, you see that you have this triangle L, H, and beta. And so this side is L, this side is H, and this is beta. So L equals H times, basically, if you can see here, cosine beta is H, right? So L times cosine beta is H, so you can find the length of each member as a function of H and beta, the only two things that are given in this problem. So that's the length of the member, that's the force in each member. And if you remember, how much is the energy stored in a prismatic bar as a result of axial load? This is the formula here, F squared L over 2EA. So in each one of them, we have to calculate the term F squared L over 2EA. This is the same as U1, this is the same as U2. Now, if I plug these F and L that I have here, you can see that it will be simplified to P squared H over 4EA cosine cubed of beta. Good? So now if I call this relation 1, and I call this relation 2, if I plug 2 into 1, what would you get? You are going to get that basically P times delta Y of point B over 2 equals 2 times this, which is basically P squared H over 2EA cosine cubed beta. And what you need to do is to get rid of a 2, get rid of 1P, and from here you can calculate the displacement of point B in the downward direction. That is going to be P times H divided by, now I made a small mistake here. Each one of them will be 8, not 4. Each one of them will be 8. Okay, some of it will be 4. So it's going to be 8. And so here what you have is 4. So you simplify and you're going to get a 2 here. And then EA and then cosine cubed of beta. So this is how much point P is going to go down based on the material cross-section. the geometry and the load. Okay, and if we do any basically other analysis, correct, we can see that that is going to be basically the idea, because here you can find one delta L here, one delta L there, and these two will make point P to not go horizontal and vertical, but you can find their beta components, correct, and add them together to get the total displacement here. And if you do so, the answer is exactly what you can see here. So you see, this strain energy method can be used to solve a simple problem like this. Hopefully this video was useful to you. I'll see you in the next lecture. Thank you.